Well, good morning, dears. So, welcome back. This is Machine Learning Lecture-7. So, let us recapitulate. In my earlier lecture, I introduced you with a very simple but elegant tool for modeling data, that is regression. That is also called curve fitting using least square method. There is a square and then we are trying to find the least value of the square, and it has various names. So what we have observed is that this was my decision, right? Seeing the data for which I am designing the predictors, I am seeing the trend and I designed the predictor like this. W0, this is hypothesis, which is a function of x. Incidentally, x is also called feature, parameterized by w is equals to w0 plus w1x. Try to remember those symbols because throughout the lecture we will use this symbol, right? So these are parameters. Okay. So here it was my decision to make it linear, and accordingly I have got the result. Nobody can get better result than me with this assumption. Now, you had some data with which you have trained, that is, we use for training purpose, and as I told that maybe some 10 days data you can keep for testing to see how beautifully you have designed your predictor, and if you are satisfied, okay, then you can confirm that, okay, this is my predictor. Having said that, this fundamental assumption here is that the nature of train of the data, when you are designing, and same predictor after design when you will use it for predict the environment, the data of the environment should have this similar train. This is throughout machine learning, this is actually the fundamental assumptions. It will never happen that from a different distribution you are designing a classifier or your predictor and you will be able to predict everything of the environment even if the data in the environment are of different distribution. It will never happen. So what will be the take home? Do it fit, best fit, and then you predict it, the depth for the month of say March or April. It will be perhaps okay, but the time May, June, July is coming, this predictor will fail to predict what will be the depth per day, a particular day. Why? Because the nature of the data or the trend of the data has changed over the time. Okay. So again, if I see, so this is local prediction. You cannot, there is no free lunch in machine learning, so you cannot globally predict, you're designing one predictor only. So again, if you want a better predictor design, so what you need to do? You need to again see the data, say this is the data for July, okay, and I see the trend of the data is exponential over the day, and this is the depth due to COVID. And then what I decide is the following, that now I will not use a linear predictor, instead I will use a cubic, I will use a quadratic curve, for example. Okay. So my predictor now will have three parameters, W0, W1 and W2. Okay. And then again same old story. So this is your theoretical value, you have data, calculate actual value, then formulate our cost function, okay, and differentiate. So that's the technique remains same. And then if you from doing that, if you find W0, W1, W2, and then perhaps this predictor will be able to predict as long as data train remains like this. I think it is clear. So we have tools. So that linear regression has that ability to accommodate various data trend. We can also design a cubic curve. We can also design nth degree curve, nth degree polynomial. Then we can design a hyperbolic type of predictor. If situation demands like that, then we can so on and so forth. We can also design exponential curve, logistic curve. All these are available, and it's my decision. Seeing the train of the data, which one I should select. More beautifully, you are expert. If you are expert in analyzing the train of the data, more beautifully you select the predictors. Results would be more appropriate. Okay, so that's the take home. And then you see, I will also show you how actually to solve. Suppose I have this kind of predictor. So y equals to this is my equation. Then how the W's can be obtained? Okay, it can be obtained by actually solving three simultaneous equations. Okay, and these three equations, where from you will get? By differentiating this with respect to ones with row, same thing, another time and making it equal to 0, making it equal to 0, 0. So by doing this you will get three simultaneous equations, and those equations are linear in nature because we are talking about linear regression. And one trick I can tell you, that even without actually differentiating, there is a way to write down the simultaneous equations. So you see, I have written it down. This is all, of course, I equals to 1 to n, I equals to 1 to n, I equals to 1 to n. N is the number of samples. If it's not written, you can write down. So these are my equations which I can get if you follow this trick. Without actually differentiating, but actually you should differentiate and get this. So multiply, so this is my predictor. Multiply this by 1, then by x, and then by x squared. So this will give you three equations, and then after multiplying, you just sum them up. You see, suppose I have multiplied it with 1, okay, and then sum them up. So I am getting summation of y equals to W0 into n. N is the number of samples, right? Plus W1 into x plus W2 x squared. Just I multiplied by 1 and then sum them up. That gave me one equation. Actually, it is obtained by making by differentiating the function with respect to W0. Similarly, multiply this equation by x and then sum them. So that gives you another equation. Then multiply it by x squared and then sum them up. That's give another equation. So these are the three simultaneous equations, linear equations. Okay. You will have to solve to get W parameters, W0, W1, W3. Same way you got W0 and W1 earlier. Okay. Now, this is very elegant method because you see there is no algorithm, there is no repetitive computation. Okay, just formula we are using, and they are linear in parameters. Okay, because these are the confusion should not be there. We are still calling it linear regression because my parameters W0, W1, W2 are linear in nature. Okay, and the moment you are putting the values of sample, this becomes simultaneous linear equations. That's why still it is called linear regression. Okay, so that's the way we can solve or modify any or design any predictor seeing the trend of the data. Is it clear? So now we are trying to tell you something more about our cost function. So with the cost function earlier is equals to hypothesis parameterized with W x suffix I equals to 1 to m is the number of the sample, minus yi square. I told you intuitively that to get an idea, that's okay, assume it as an error and then square it so that error will be positive, but it has one more deeper meaning why we are squaring, that we are going to explore. So we have squared it, and for mathematical convenience, let us divide it by 1 by 2m. Why we are doing that, you know, because you will have to differentiate. By differentiating, 2 will come here, 2 cancels out, and then m number of samples, sample m is constant, so we are dividing it by m also, so that the expression will be simpler. Okay, unnecessary terms will not be here. So that's the only thing you need to know. Henceforth, we will use this as my cost function. Okay, always. So let us see what is the deeper meaning of squaring of designing the cost function like this. Okay. So here we are trying to explore the nature of the cost function. Okay, and what actually hypothesis is computing, and what cost function nature with is exhibited, right? Take the example, hypothesis again, the function of feature, x is called feature, function of x, parameters by w, w0 plus w1x. Now since I suggest all of you should do by hand calculation, so for doing hand calculation you can just, because we are trying to understand the nature of cost function by making it square like this. Okay, so without loss of generality, let us take w0 equal to 0 and fix some values of w1. Okay, so this is a function of x. Now I can plot, okay, 1, 2, 3. Okay, so this is 0, so and this is equals to 1. So then my hypothesis is actually equal to x. So this is y equal to hypothesis equal to x curve passing through the origin, and then I can calculate the functional value. Okay, functional value j, which is equals to 1 by 2m. Here, say we have taken 3 sample, 1, 1, 2, 2, 3, 3 for simplicity, so that we can do by hand. Okay, so what is this j? 1 by 2m, 0 square, because 1 minus 1, okay, 2 minus 2, 3 minus 3 square, so 0. Okay, for w0 equal to 0 and w1 equals to 1. Is it clear? This is my function, hypothesis function or predictor, and which is passing through 1, 1, 2, 2, 2, 3, and naturally there is no error, so it is becoming 0. Now let us suppose I am changing W1 values. Now I am making W1 equals to 0.5. You can make it 0.25 and 1.15, anything, 0.5. Okay. So now predictor becomes 0.5 into x. So for any x, I can now calculate 0.5 minus 1 predictor is telling 0.5, actually value is 1. So this is error. Predictor is telling 1. Okay, and actual value is 2. Okay, got my point? 0.5 into 2, actually predictor is telling 1. 0.5 into 3, 1.5, and actually predictor is telling me 3 square, and very simple, of course. And then you can calculate the value. So J value is now this. Okay. So for plotting, you can generate as many values for J. Okay, for different W1 values. Okay. So for like that, okay, 1.5, 0.25, and then let us see we are making both of them equal to 0. Then what will be the my predictor will be just x-axis, okay, and then my error will be 2.3. Now let us try to plot, okay, that error function or cost function versus parameter W1. Okay. So since it is simplified, only one parameter I have taken. I can show you by plotting. Okay, that's very important to understand. Okay, so if I plot, then you can see the function nature is quadratic. This is convex function. Okay, convex. So J is convex in nature. It's beautiful. There is a convex theory, convex optimization theory behind machine learning. Okay, and those who will take up this course afterward, fine. But my duty is to tell you, this is wonderful nature. Why wonderful nature? Because I have only one optimum point. It is not like this. Function is not like this. I do not have multiple optima. The function, by constructing the function in this fashion, okay, guarantees you that it will be always like this. Okay, so this is a taking only W1 parameter. One parameter in 2D I can make the plot. If you take two parameters, then still you can plot, and it will be a bowl shape. Okay, like this. The nature of the curve will be like this. If I take okay, so that's the story. So this will be again a convex. This is convex in nature. Okay, and what is so fun about convex curve? Because when I am solving optimization problem, I have unique value, okay, which is here 0 value corresponding to parameter 1. The value of JW is 0. Okay, it could be anything, but the nature of the objective function will remain same whatever we do if it is designed like this. That is hypothesis parameterized by W x minus y squared. Okay, so it is, although intuitively it can be thought of that you are trying to make the error positive always, but the inner meaning is that we want J function should be convex in nature. Okay, so we'll continue our discussion. Very simple, but need to know, and I suggest that you should practice. And now you will get some simple problems, assignments. Please do assignments religiously. Okay, thank you for your attention.